Hi everyone, thank you for having me. I'm Xiangpeng Hao. I'm final year PhD student at the University of Wisconsin-Madison, and today I'm going to talk about LiquidCache, a new kind of cache that understands both compute and storage. And this work is sponsored by, well, not sponsored, like part of sponsored by Influx Data, Poplan, and SpiroDB, and of course, taxpayers of Wisconsin and the federal government. Okay, so modern data systems, we have compute and storage separated in the cloud, and that gives us all the scalability and elasticity we have. But that creates a significant performance gap because every time we run a query on compute node, we have to course over the network. And S3 initial latency is 100 milliseconds just for the first byte. So that creates a lot of performance gap. And the universal solution has been we want to add cache. And we can add cache everywhere, but it has been one of the most important components in our system. So in the cache, it is supposed to understand and bridge the compute and storage, but existing cache are dumb. They don't understand neither side. So this means on the storage side, we have S3, then we just the cache just mirror whatever is cached in S3, even if the storage the data we store in S3 is not super optimized for the query execution. We just cache it as is, serve it as is, and we miss a lot of opportunities there. And on the right-hand side is compute. Again, we don't understand what the compute is trying to do. If we want to read a column, like from user column, we just blindly serve entire column over the network, which cause a lot of network traffic, and that's not great. So the reality is we have this cache, but it's massive waste. We spend a lot of CPU resources on the the bytes we actually don't actually use, and massive CPU cycles to decompress, decode data that we don't actually use. So LiquidCache wants to build a cache that understands both the storage and the compute. And that is a key principle of LiquidCache. And we think this is a great opportunity today because the cache, we want to build cache as a separate cache service which have the CPU bundled, have this memory that we can actively understand the data, actively understand the intent of the compute. And that means on the storage side, the LiquidCache is going to understand the data you have in storage. This means we're going to actively transcode and re-encode the data into an optimized format such that it can serve the computation more efficiently, so that you don't have to switch to a different file format just to benefit from the state-of-the-art encodings. And the best part of this is because it's in a cache layer, we are free to evolve everything, evolve adding a new encodings when we see fit, or remove encoding if it's not super stable, without worrying about the ecosystem compatibility. Because we transcode the data, everything stays within the cache, and we just stay compatible with the ecosystem. And on the right-hand side, this LiquidCache, we're trying to understand compute, such that it understands what filters you're going to run on the data and what aggregation you're going to run. So it allows the computation server to push down those operators down to the cache server so that we can run those operators locally with data. So we don't have to move all the data over the network just to run the simple filter aggregations. And we also implement all this as a DataFusion optimizer rule, so you don't have to change a new file format, you don't have to change a new query engine, just hook in and everything just works. So next, we're going to zoom in a little bit, see how it works by understanding storage and compute. Okay. So to understand why we want to re-encode data from the storage, we have to understand how the hardware has evolved over the last decades. 10 years ago, the blue line here shows the storage bandwidth, basically how fast we can fetch data from storage, and the green line shows the decompression throughput, basically inflate the data so that we can feed to the query engine. 10 years ago, those two lines are pretty close, and usually the storage I/O is the bottleneck, And that's when we design the Parquet format. We want to highly compress the data such that we want to trade CPU cycles to save IOs. But over this decade, we have seen that like the more slow basically slows to scale, but the IO has keep doubling their speed bandwidth every few years. We have NVMe, PCIe 3, 4, 5, and VC6 in a few years. So the gap becomes larger and larger. The equation here has flipped. So we are no longer waiting for the I/O to do the pre-processing. We're waiting for the CPU to turn those bytes into useful value that we can process. So in today we have to like in our evaluation, like a simple typical filter pushdown case, we found that actually 90% of the time spent on filter pushdown is on decoding the data, and actually only 10% of the time is spent on evaluating the filters, and that's a massive waste. Okay, so the natural question is, or the question is, if decoding is a problem, why don't we just make a new file format, right? And the industry and the researchers has definitely tried. We have invented a lot of new file formats like BetterBlocks, Vertex, Nimble, or Lens, and Fastlanes, F3. Or we have new encodings and new formats coming almost every year. But look at the adoption rate. It's still pretty low. So why the problem? The problem is choosing a file format for our data is not just about decoding speed. It's not just about performance. It's about something else. Like for example, even in the Parquet, a minor updates to Parquet took years of ecosystem coordination. We need to make sure every writer and every reader understand the data we write in, so that we don't risk breaking the compatibility. We don't risk breaking the data pipeline we already have. So a complete rewrite of a completely new file format means we have to rewrite the petabytes of data we already have, and it means we are going to break the data pipeline, we are going to break the compatibility, and also break the trust. And the trust Parquet has been building over the last decade. So, and also to be fair to Parquet, it's actually a okay file format for the storage. It's actually so you have it's long-term archival. It's very stable, open, stable governance, and you know it is going to be around for the next 20, 30 years. And so that's it's actually a good fit for the storage. So here we have this dilemma that we're likely going to deal with Parquet for the next 20, 30 years, but we in the computer side, we desperately need something faster for for query processing. And how do we resolve that dilemma? And the problem of all this dilemma is that we have this assumption. We basically have cache working for half a century since we have computer science, that the cache is going to mirror whatever in the storage. So if we have Parquet in S3, then our cache is going to cache the Parquet data. And that mindset basically prevents a lot of opportunities we can have. So LiquidCache try to be very different in a way that we argue we try to cache the logical data, not the physical representation. This means that we don't care about what you store in the S3. It can be Parquet, it can be CSV, JSON if you want, but the data in the cache is being actively transcoded and transformed into a format that tailors to a workload, tailored to the need of computation. And this way, we kind of completely decouple the data in the cache and the data in the storage, and allows us to evolve the cache more freely. So what's special about liquid format? Liquid format is informal format. It has no permanent specification, unlike other file formats, because we believe we have and will have new encodings emerging every year. This means that every year if we switch to a file format today, then next 5 years, that file format will be outdated. So in LiquidCache, we want to make the liquid format informal and stays only the cache, one in a format that we have full control of. We don't leak the data to the elsewhere. That means we can easily add and remove encodings without worrying about compatibility. And on the bottom side is one example of LiquidCache, which we have this flexibility of transforming the data into the form that better fits the query needs. This is a string column without compression. It's in arrow data. It's like 12.9 gigabytes. With dictionary encoding, basically deduplicate the strings. We cut down to 5 gigabytes. And the bit packing is like bit pack the dictionary keys goes to 4.7 gigabytes, and we can add FST encoding to 2 gigabytes. And the best part of this is it's a cascade encoding. We can transform the data into any form we like. For example, if we go to the left spectrum, the data is less compressed, but it also means we do less work to do the query processing. This means if some piece of data is very hot, we don't want to compress it. And on the other hand, if the data is super cold, then we're going to push the data to the right-hand side of the spectrum. It will be compressed more, but unlike the conventional file format where we have to choose one compression level for the entire file, LiquidCache is very fine-grained and adaptive to the query processing access patterns, so you can adjust encoding level based on the access frequency. So we have covered the left-hand side. Basically, LiquidCache understands the storage by re-encoding the data in storage into a format that is informal, that can leverage the state-of-the-art encoding, that can adapt to the query access patterns without breaking the ecosystem. So you can still use the file format you like. And now we're going to switch gear to the right-hand side. How does LiquidCache understand compute? So we do this by filter pushdown. Filter pushdown, I believe all of you know this because we're in the database area. So basically, filter pushdown says we want to push down some of the filters down into the storage layer. That's the conventional definition. So without query pushdown, let's say I want to read the user ID from the cache, then the cache is going to read the entire ID column and send to the cache. But with and I get all of this data only to filter like 90% of it out. So I immediately discard all of the 90% of data transferred over network. But LiquidCache will try to understand what the computation tries to do. The computer will push down the filters or lightweight aggregations down into the LiquidCache level so that we can co-design the filters aggregations with encoding so that we can have some optimization, like we can skip some of the decodings, we can evaluate filters directly on the encoded data. So that will help us reduce the CPU burden on the LiquidCache. For example, here's a very simple example. In LiquidCache, it's much more convoluted. But here we have a filter we want to find. Department equals computer science. And normally, if we in the parquet, you have to decode, read the column and decode it, make it into an arrow format, and then you want to evaluate the filters. But here we are aware of, okay, we already compressed the data using dictionary encoding. So we first look at the dictionary, is computer science, and we found the target key is 2. And then we're going to scan the key arrays, that is integer comparison instead of a string comparison, so that we know which items pass the filter. And this way, this is a very simple, almost too simple comparison, but the idea is because LiquidCache has this spectrum of encoding, spectrum of cascade encodings, we always want to decode the data to the right level such that it's enough to evaluate the filters. So we never have to, most of the case, we never have to decode all the way decode to the arrow format just to evaluate the filters. So fast decoding is not decoding at all. And the second part is the eager materialization. For example, let's say we want to find a column username equals to A and the department equals computer science. That's the two column evaluations. The traditional way is we fetch the column 1 and fetch column 2 and decode both columns, and then we filter both to get the results. But LiquidCache can do more fine-grained selective decoding. We first decode column A, and we decode all of the columns and then apply the filter A. Then we probably find only 5% of the rows passing that filter, so that we're going to pass that filter mask down to the column 2, so that in column 2 we only need to decode 5% of the rows. That will save us more decoding time. Okay, so we talk about LiquidCache, how we connect with storage, and how LiquidCache cooperates with compute. This is a typical LiquidCache setup in our experiment, where LiquidCache is a separate dedicated server, and you talk to the object store, which is at least 100 milliseconds if you use S3. And the latency between LiquidCache and compute is usually less than 1 millisecond because the LiquidCache server is deployed right next to the computer servers, so within the same cluster. And in this setup, LiquidCache uses filter pushdown to reduce network traffic, and it can independently scale LiquidCache. Like if you want more memory, just scale LiquidCache. And there's no special hardware needed, just some standard EC2 machine on AWS, and you're ready to go. One slide on the decoding. So on the top side is the Parquet. We basically measure the pushdown speed, and in Parquet this is take 27 seconds, and most of the time it's decoding. And Arrow here is basically a case where you have no decoding because Arrow is already ready for DataFusion query processing. But Arrow spend a lot of time on memory store, meaning that Arrow data is like 12 gigabytes. Then scanning those 12 gigabytes also take a lot of time. But LiquidCache is like 2 gigabytes. Then you spend some time decoding, but scanning 2 gigabytes is much faster than scanning 12 gigabytes. So the optimal case here is like basically we only spend compute and without any time on the I/O, on the decoding or the memory store. So we are pretty close to Arrow and not too far away from theoretical or optimal. So also you might argue that transcoding our data is actually pretty expensive, right? Because it's basically when you're transcoding data, you want to decode the Parquet data entirely. And that time is actually, in our experiment, is actually completely hidden by the network I/O. Because on a cache miss, this means you always want to read some data from different cluster or from S3. That time is like, if it's within the same cluster, it's almost 10 seconds. If it's cross data center, it's like 15 seconds. But transcoding that data is only 2.2 seconds. That means while you are waiting for the next batch for network I/O, you can essentially doing the transcoding for the previous batch. So the effective latency, like a transcoding overhead, is high. Okay, so if you basically that means if on a cache miss, you almost see no extra overhead when using LiquidCache transcoding. And on a cache hit, you already hit the data in the LiquidCache, so it's much faster. Okay, so that's the LiquidCache. We had talked about on the left-hand side, if you transcode data into a better format, and it allows you to stay with the Parquet ecosystem. You don't have to use a new file format. And on the right-hand side, we talk about the pushdown and how we co-design the encodings and the filter evaluation with evaluation. And the LiquidCache is built on top of Apache DataFusion, and you can just hook in as a data provider, and you're ready to go. It's also open source. Yeah, thank you.